Can I get a hello? Hi! All right, this is SecDSM night. I'm going to be talking about Linux Firmware Database, which is a project I built in December after doing the same repeated analysis like 4 times over the last couple of years. So I just put all the data together and published it on the internet so that everyone can have it and no one has to do a bunch of scripting. My name is Nick, and I'm a threat researcher at Hewlett-Packard Enterprise, or HPE Aruba Networking. I do stuff with things. I focus really heavily on firmware, specifically like Linux-based firmware, which is not exactly what I'm talking about tonight, but for what it's worth. I am a proud SecDSM member. Who else is a SecDSM member? Everyone should be raising their hands right now. You are a member if you are here. Okay, so let's talk a little bit about Linux firmware. Linux firmware is a Git repository that's maintained and hosted on kernel.org by the Linux Foundation. It's basically just a big directory full of binary blobs. Where's Nate? Anyway. It's a big directory full of binary blobs that are then loaded onto component firmware once the system boots or the component becomes available. So what does that mean? Like when you plug a Wi-Fi dongle or like an Ethernet PCI card into a computer, a lot of times it requires firmware to run and operate normally. And that firmware is loaded into the component peripheral DRAM at runtime or whenever the device becomes available. So basically, the kernel sends over the PCI bus these files in this repository. It gets loaded into DRAM on the card, and that's how the card knows what to do. It's the instructions that power the card and allow it to function like it should. This has a lot of advantages because then you can update the firmware fairly easily by submitting a patch to this repository. It then gets pulled into the next tag or update whenever your distro gets updated, and you get the newest, latest, and greatest security fixes and features and all kinds of cool stuff as part of this model. Really, like, there's a lot of different kinds of device support for like Linux firmware, but like, I'm only familiar with the networking stuff, so that means like Wi-Fi dongles, Ethernet adapters, things like that. It doesn't have to be just Ethernet. It can be like whatever that fabric is that they use to connect supercomputers. I can't remember the name of it off the top of my head. This repository is maintained by Red Hat as part of the Linux Foundation. If you want to submit a patch to this, you have to go through Red Hat to get it in there. And the Linux-firmware repository is included on almost every single Linux distribution out there. There are some notable exceptions that do not include Linux firmware, specifically because the blobs in this repository are proprietary, right? Like, there's no source code with them. They're not open source, and that makes a lot of people in the open source community very, 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 very angry. So there's a few distributions that do not allow Linux firmware to be in their distribution. So I built this data set around this repository. And really, I just took a bunch of metadata measurements of the binary files. And I managed it into a big JSON object that I posted on the internet. And all the scripts and data are all in this repository on GitHub. So it's basically a self-contained project, right? Like, not only there's no server-side component to it. Everything is in the browser. Everything's loaded onto a web server and served over HTTPS from lfwdb.com. So why did I build this? Like I said, I did this kind of analysis like 3 times in a row, and it was over several years, and I was just like, Man, I gotta just do this once to be done with it. The other part of this is, like I said earlier, these are proprietary pieces of code, and I wanted to kind of raise awareness of what is inside of them. Like, what is going on in these firmware blobs that no one's really ever looked at in depth. And as part of that, like my future work or what I would like to eventually do with this is to gain a better insight into what's going on with these blobs. Like what do the instructions do? What are the base load addresses? How can we reverse engineer these to develop a better understanding of what this proprietary code is doing in the open source ecosystem? So the scripts I developed are a three-phase process. The first phase is to understand what computer instruction set architecture the blobs use, right? So like ARM or MIPS or PowerPC or any of the other 8-bit microprocessors. There's a tool built by Airbus SecLabs, sorry. And this tool is called CPU-Rec. It takes binary data and runs heuristic algorithms over it to output what kind of processor it thinks the binary data is built for. And so this is a long process, right? Like running CPU-Rec on one megabyte file will take 15 to 30 minutes. So you can imagine over like 3,000 of these files that the process of running the heuristic algorithm in CPU-Rec does take quite a while. And that's what I was running into, right? I was spending a lot of time running CPU-Rec and repeatedly doing it over and over again. And eventually I just got fed up with it and I said, let's do this once and no one has to do it again. And that way we don't have to waste computer resources to continuously run. Yeah, clap for me, that's great. Yeah, thank you. And so the second phase is that I run a couple of other tasks against the files in the system, like I compute a SHA-256 checksum, and I run the Linux or the GNU file command to get an idea of what the file command thinks the blob is. And I include all that into a CSV file, and then the third step is converting the CSV to JSON, which is very, very quick, even though I'm using single-threaded Python. So once the data is in JSON format, I try to run R2 over it, and R2 is like Ghidra, but from the Linux command line. It's a disassembler that has a lot of support for different instruction set architectures. So I try to run disassembly over like ARM, MIPS, and a couple of other ones. The 8-bit microprocessors, as you can imagine, don't disassemble well because no matter what, they're going to disassemble to something, even if the data's garbage. So I try not to, I don't disassemble any of the 8-bit microprocessor architectures. And I just stick to the 32-bit microprocessors and processors to avoid junk disassembly. And really, the disassembly is not there to reverse engineer. It's there for whoever is coming to consume the data to perform a quick heuristic as to whether or not the file is the instruction set architecture that my data claims it to be. So what I mean by that is, like, if you take a look at some of the disassembly and you see it doing all kinds of weird things that like no program would ever do, you know that the data is not computer instructions. You know it's encrypted or compressed or something like that, and there's not a lot of reverse engineering you can do in its present form. So after I've run the disassembly, I commit the data to the repository and I push it up to GitHub. Then GitHub does a bunch of stuff and deploys it out to the web. The web interface is the primary way for people to consume the data, for humans to consume the data. I built this Vue.js interface that was really, really ugly. It's just for reading the data, basically. By the way, if you are good with style sheets and you want to help an open source project, I know of one that could use your help. So just keep that in mind if you want to contribute back to the community. The Vue.js application would not be useful if it wasn't sortable and filterable. So I'll show you what this application looks like in a minute, but if you want to look at it right now, it's posted at https://lfwdb.com. And you can see just how ugly it is if you want to right now. Yeah, I kind of jumped the gun on this slide, I guess. So this assembly is hit or miss. Sometimes it disassembles to junk. Sometimes it disassembles quite well. And the idea is to be able to know which files are not encrypted, not compressed, instruction-based files that can then be loaded into Ghidra or R2 or the IDA Pro, things like that to continue the reverse engineering process. The disassembly with R2 is automated as part of the build process for the project, and it does not take very long. So I just included it. It was like 12 lines of code to hook up R2 with the rest of my data. So it's really quite easy to implement. Where does this project run? Well, all of the data processing occurs on a little bitty NUC in my basement. So this NUC is like a i5 12th generation processor. It's only got 16 logical cores. It does have a lot of RAM, although you don't need a lot of RAM to do this sort of operation. I think 16 gigabytes on a server would probably be enough. The NUC only has 256 gigabytes of disk space. This repository is large. The data directory alone is a gigabyte, but it compresses very well down to about 256, 300 gigabytes or megabytes if you're cloning it over the global internet. The upload is a 1 gigabit fiber uplink. I don't even know why I included that. Why did I self-host? Because doing this in the cloud would have been like 10 times as expensive. And it would have been more crap for me to maintain, and I didn't want to deal with it. All right, so when we start looking at the data and trying to figure out what it's telling us, one of the extraneous operations I performed over the file data is the Shannon entropy calculation. And Shannon entropy calculations are a range of 0 to 8, float data, floating point values. So the closer you get to 8, the more random the data is. And anything above 7.5 is considered cryptographically secure, like as a CSPRNG. So anything from 7 to 7.5 is still probably encrypted, maybe decently, maybe not. Anything from 6.7 to 7.0 is probably just XORed with a couple of bytes. So there's different levels of cryptographic protection on some of these files. And there's a correlation between heavy cryptographic use or high Shannon entropy values and what vendors are using for their firmware. So like, for example, Mellanox, almost all of their firmware is about 7.9 in terms of Shannon entropy values, which means it's highly encrypted. And that just means that they're using something like AES 256 to encrypt the blobs that they're then uploading to the Linux firmware Git repository. Yeah, so one of the side projects I took off of this project was I found that there was encrypted zip files in the Linux firmware repository. And so these function just like any of the other firmware blobs. They're downloaded to a PCI card on boot or on component load, and that means the card has to decrypt the zip files and extract the firmware from those zip files. So I did a lot with this. I tried to extract the hashes of the files using John the Ripper, and then crack those zip file hashes using like a big GPU cluster, no success. I attempted to physically extract the SPI ROM data and other like flash NAND data off an actual copy of the board, and that didn't lead anywhere. I couldn't get flash ROM to recognize the SPI NOR chip that was on board of the card. And I also attempted, as part of the data extraction from the actual PCB, to dump the EFI and BIOS option ROM data off of embedded storage, and I couldn't get that to work either. Like it just nothing worked with this. I think that's probably because the card was from 2010. It was a gigabit fiber, a 10 gigabit fiber card from like 2010. So it was really easy to get on eBay for like $10, but like I couldn't. It was so old, and my skills are so bad that I was not able to actually accomplish the goal that I set out to do with it. So that's an open problem. If anyone wants to fund a research project, I know where you can get some of the PCI cards too. Yeah, so this was a really short presentation. Here's some of my contact information. If you want the contact information, it's here. Google if you want the link to my YouTube channel. If you are doing machine learning visual recognition, that's the link to my YouTube. Yeah, so that's for you, Google. Does anyone have any questions? Oh, yes, yes, sir. Yes, sir. Yes, sir. And before I get off stage, let's take a look at what this web interface looks like, so you can see how hideous it is. So this is the actual live site hosted on the internet. You scroll down, and you can see the first thing you have to do is select a tag. This corresponds to the Git tags in the Linux firmware repository. They go back to 2019. There's about 50 or 60 of them, and I believe I have all of them in here at this point. So if you want to look at historically what firmware has been removed, added, this is a good way of doing that. So if we select the latest tag, it loads 3,500 firmware images or firmware files from the Git repository. And you can see here that there's like the file name, there's the architecture, there's like what it thinks may be a portion of the file's CPU architecture, the length. This is very specific to CPU rec. This is the file data, GNU file output, the Shannon entropy, the disassembly. So what does the disassembly look like? Well, it looks like this. Yeah. So this is really no good to a reverse engineer other than providing a quick heuristic over whether or not it disassembled properly. And that's all it's meant to do. It's not meant to be an in-depth reverse engineering process or tool. So the other thing I guess we can show is the, let's see, the sorting of the Shannon entropy. Okay, so if you look at this, you can see all of the encrypted firmware, the firmware that has high Shannon entropy values, and yeah, it's stuff like this. You know, you click on this, it takes you to the linuxkernel.org Git repository on the web and shows you what the hex dump of it. So just kind of a tool if you want to poke around and see what's in the firmware that's running on your Linux distribution. Or if you're wanting to do more in-depth analysis, clone the repository and check out the scripts. And all this data can easily be rebuilt using the scripts in the repository. So there's nothing special about what I've done. It's all public now. Anyone could use this to rebuild the data set if they want to. And with that, I will revert back to questions. Awesome. I put you all to sleep. That's great. Great news. Great news. Thank you, everyone.